Okay, hello everyone, and welcome to United Nations University Institute for Water, Environment, and Health Science Talk Series in our 30th anniversary year. My name is Alexander Timer. I'm UNU-INWEH's Knowledge Management, Events, and Operations Assistant, and I'm delighted to be your host for today's Science Talk. For those of you joining for the first time, our Science Talk showcases the diverse, policy-related, relevant and interdisciplinary research of UNU-INWEH and our global network of experts. These sessions are designed not only to share cutting-edge science, but also to explore how science translates into real-world solutions for water, environment, and health challenges around the globe. Today's session, like all of our talks, is being recorded. The video will be made available in an open access format following the event, and you can find recordings of all of our previous science talks on demand via our website and YouTube channel at unu.edu/inweh/science-talks. As always, we will conclude with an interactive Q&A session, so please feel free to post your questions in the chat at any point during the presentation, and we'll address as many as possible towards the end of today's session. It is my great pleasure to introduce today's speaker, Dr. Varun Tiwari. He's a geospatial data analyst and postdoctoral researcher at Clark University. His work lies in the vital intersection of remote sensing, AI, and climate resilience. With over 9 years of international experience across South Asia and the US, Dr. Tiwari specializes in using machine learning and cloud computing platforms like Google Earth Engine to process large-scale Earth observation data. His current research focuses on advancing global land surface albedo products to better understand environmental sustainability. Dr. Tiwari earned his PhD in geospatial analytics from North Carolina State University, focusing on flood monitoring and agricultural mapping. Throughout his career, he has collaborated with major global organizations, including NASA, USAID, USDA, and CGIAR, to build operational systems for disaster response and sustainable agriculture. He's also a passionate mentor who has trained numerous professionals across the Hindu-Kush Himalayan region in GIS technologies. He's combined technical excellence with a strong sense of societal purpose. So please, everyone, join me in welcoming Dr. Varun Tiwari for today's Science Talk. The stage is yours.
Thank you, Alex, for the great introduction about me. Good morning, good afternoon, and good evening to people joining from different parts of the world. It's a pleasure to be here. To start with, I'm going to remind you all about a beautiful childhood memory, a poem that you guys must have recited in your childhood. Twinkle, twinkle, little star, how I wonder what you are, up above the world so high, like a diamond in the sky. Now imagine a situation, what if the stars in the sky is not visible? What if we cannot step out to see the star for stargazing because of the unlivable conditions, because of climate change and all. Sounds scary, right? But it's not the future threat. It's a present reality, and many regions across the globe are facing these challenges where there is no clear sky conditions to witness twinkling star, or even to or the places are unlivable to live on the earth. So that is why it is very important to monitor the planetary health. And in my today's talk, I'm going to talk about how we can leverage space-based technology, mainly the satellite images and state-of-the-art artificial algorithms to not only monitor planetary health, but also predict the future about the health so that proper interventions can be taken. I'll be mostly emphasizing on understanding the Earth's energy balance and ecosystem through the use of satellite imagery and machine learning algorithm. So this is a picture which gives the overview about or a concept called planetary health and how planetary health are interconnected with human health and environmental health. When we say planetary health, we may think about clean water to drink or for agriculture activities, clean air to breathe, stable climatic conditions or livable conditions to sustain life, safe communities to live, which doesn't have flood and drought or any other catastrophic um, events. So that's what all we can think about, right? But the thing is, because of the climate change, and there is a rising global temperature, and because of the rising global temperature, there's a extreme weather events, catastrophic events like floods and droughts are more frequent and happening worldwide. There's also melting ice are melting and rising the sea level. And these climate change is impacting different thematic areas and subsequently affecting the human beings and the environmental health. One is the agriculture and food system. Climate change has caused catastrophic events, which is causing reduction in the crop yield, threatening the food insecurity in many regions around the world. Uh, Similarly, drought and flood events are also hampering the crop productivity, causing either complete crop loss or reduction in the yield. Also, urban cities are facing these flood problems and urban heat island problems, which are making these places unlivable for human beings. Same scenario is also happening in ecosystem services, where not only humans but even birds are migrating from one place to another because of the unlivable conditions. So, in nutshell, planetary health is directly impacting human and environmental health, and there is a need to monitor the health of the planet, so that we can make um, mitigation measures to counter that changes which are happening and making this world a better place to live. Now, to understand the planetary health, one of the most important aspect to understand is the Earth energy balance. How the planet Earth is livable place in the universe, and to understand that what has happened, how it happens is when is from the sun energy, incoming solar radiation, when it enters the atmosphere of the Earth, some of the amount is reflected back to the space, around 30% by clouds, atmosphere, and surface albedo, whereas the majority of the solar radiation or solar energy reaches the Earth and interacts with different land use, land cover, or different objects on the Earth, and produces different heat, which are latent heat, sensible heat, and ground heat fluxes, important for net radiation, or I would say energy availability. When I say sensible heat, it means that the heat which is directly responsible for altering the temperature, increase or decreasing the temperature. Latent heat is something which doesn't cause temperature increase, but it is responsible for evapotranspiration, which governs the overall climate, formation of clouds, precipitation regime, and other things. Third one is the ground heat flux, which is basically a heat which is stored in some form, in the energy stored in soil or maybe ocean or built up surface, and slowly release and slowly get released. So you might have witnessed, especially in the summer season, during the daytime, the outdoor surface becomes very hot, and during the night time, the heat is radiated from those surfaces. It's because of the ground heat flux. And um, what happens is, like, because of the greenhouse gas emissions, um, this energy balance gas disrupted, causing uncontrolled earth temperature and climate. And because of that entire Earth energy balance gets disrupted, result in more catastrophic events, um, floods and droughts, and urban heat island. So therefore, it is very important to monitor the Earth energy balance to make it stable, so that this place is more the uh, planetary health is more sustainable. To understand the Earth energy balance, one of the concept is albedo, and how we define albedo is amount of reflected solar energy coming from Earth, how much is reflected back to the space versus how much is the incoming radiation. It is mainly range between the value 0, 1, where 0 means almost all the energy is reflected. There's no reflection; it's all absorption. And when it is close to 1, that means all energy is reflected back to the space. And different objects or different land cover reflects energy in different ways. For example, here, snow and ice is light surface, so most of the energy coming from sun reflects back to the space, whereas only 10%, around 10% of the energy is absorbed by snow and ice. On the other hand, if we consider the darker objects like roads, ocean, even forest, because of the darker objects, the only 5 to 10% of the energy or incoming solar radiation energy is reflected back to the space, and most of it is absorbed by these land cover, and which produces heat and subsequently results in increasing land surface temperature and contributes to global warming. So why albedo matters is, so albedo is very important for climate regulations. Um, Albedo control how much solar energy is absorbed and reflected, as we can see, as we have seen. In terms of climate modeling and other scenarios, albedo is one of the major input to model climate and see how climate change is going to affect humans and other creatures in the near future. It also albedo also governs the surface temperature. We might see that these days, especially in urban cities, people are painting their rooftop to white from black, and the reason is to control the surrounding surface temperature, both in terms of indoor temperature and outdoor temperature. As I said, the latent heat also responsible for the water cycle, because it is responsible for um, precipitation, evapotranspiration. So it affects the entire snow, ice, and water cycle of the Earth. Albedo is also very important for soil moisture photosynthesis, which results in crop productivity, and those kind of things. So maintaining the stable growth conditions are so albedo is very important for maintaining the stable growth conditions. So there are different types of albedos in the world. The albedo is mainly classified as white sky albedo, black sky albedo, and blue sky albedo. When I say black sky albedo, it assumes that it's a clear sky condition and there's no atmospheric scattering, and whatever is coming from the sun is reflected in one direction. And this is very useful for VADRF based modeling and solar geometric studies. Whereas white sky albedo assumes that there is a complete diffuse illumination because of the clouds and atmosphere. And these kind of albedos are mainly used for climate and radiation studies. Whereas the third one, like the blue sky albedo, is the most realistic kind of albedo, which is a combination of black sky and the white sky albedo. And most of the remote sensing satellite observations uses blue sky albedo. The albedo also can be classified based on the broadband electromagnetic spectrum. So these are like broadband albedos, which captures the radiation in broadband, includes UV visible and near infrared regions, whereas the narrow band albedo captures the albedo in specific wavelengths. Typical example is Sentinel-2 images or satellite bands in which the reflectance is being captured. And these albedos have different applications, from climate modeling to vegetation monitoring. So these are some of the application of the albedo. As I also already mentioned, that urban height island is one of the thing which is governed by albedo. And what urban island means is, usually in city areas, the temperature is far more or far warmer than the suburban areas, because the heat gets trapped inside the city, which creates a island kind of effect, a clear-cut boundary between hotter areas and cooler areas. And one of the how albedo governs this changes is, the darker objects in the city, like rooftop, absorb more heat, which increase the surface temperature. Similarly, in agriculture, one of the application of albedo is to monitor the crop health and also to forecast crop yield. The other application in agriculture area is to monitor crop conditions and crop health. The third one is basically tillage versus non-tillage crop cultivation thing. As we know that tillage actually increases the darker objects, and which results in less albedo, making the surface warmer, whereas the no tillage condition will result in high albedo, reflecting all the solar radiation to the back to the space, causing lower surface temperature. Um, Similarly, renewable energy is one of the application area where albedo governs or plays a major role, uh, specifically in site suitability for solar farming. If we know the area which has more solar illumination, then we can decide where to place our solar farms and things like that. Albedo also is very useful in climate modeling, and most of the physics-based models use albedo as one of the parameter to simulate future climate conditions in different scenarios, emission scenarios. This is an interesting example which I want to share. There's a myth that afforestation helps in reducing the global warming, because um, it lowers the temperature. But it's not a situation, because there has been studies which has been done in the past, which suggest that the warming and the cooling impact depends on the location and the climate. And there's an interesting study by QE et al., which suggest, and also reflected in IPCC report from 2001 to 2023, suggests that the polar regions specifically, which are close to poles, and which are very cold and dominated by snow cover, where the afforestation actually warms the temperature, result in increased temperature. Whereas in other regions which are dominated by which are close to equator, have cooling effect. And the primary reason is because the forests are darker in nature, so it absorbs all the heat coming from the sun. Whereas the snow has high albedo, it reflects all the radiation and throws everything back to the space. So to monitor albedo, there are different things. One is the like how albedo monitoring or climate modeling was done in the past is they used to have collect ground data and then like temperature, rainfall, and those kind of things, and run physical based model to come up with the climate simulation. But how satellites can help here is satellites provide synoptic view. It also provides large coverage with global repeativity, daily repeativity varying from sub-daily to monthly. And there is historical data, ample amount of data, which is also available from 1975 onwards till now. And with different satellite sensors, different kinds of data sets are available in different wavelength regions, like in optical, in thermal region, in radar region, uh, and those kind of things. So when remote sensing data or satellite data, when combined with artificial algorithm, mainly the shallow machine learning or deep learning algorithm, we can derive trends, historical trends, what has happened in the past, and not only that, we can also predict future, what is going to happen in near future based on the past trends. So all this analysis is possible only because of the ample availability of satellite data set. But the challenge with the satellite data is the resolution, the spatial resolution. And here is an example of the problem here. There's a study from Chen et al. 2023 uh, showing this is a site from one of the glacier, and you can see on the left, figure A is actually the false color, true color composite of Sentinel-2 data, whereas B is actually the predicted or estimated albedo at 10 meter spatial resolution, and C figure is actually the um, land albedo information from MODIS, which is available at 500-meter resolution. Um, so most of the satellite data sets acquire or collect the information about albedo from 500-meter resolution to 1 kilometer resolution, which is very coarser to capture the peculiarities in detail. Here you can see the zoom in version of this small area here, and you can see that on the right side figure C, we don't have, the resolution is too coarse, where it's not able to capture the variability of albedo in different land cover classes, mainly the snow, whereas in figure B, it's able to capture those variability in the high resolution product, albedo product. So one of the limitation, as I said, about the albedo product is only coarser resolution albedo products are available with daily coverage, um, um, which is insufficient to capture the fine scale landscape heterogeneity in cities, forests, agriculture fields, and in urban areas. The second limitation is the temporal and thematic coverage. Although some researchers have attempted to use AI and satellite data to generate high resolution albedo product, but they only focus on single class like urban, which lacks revisit because training AI model also comes with a cost, because there is a high computational cost associated with it, and which also like restricts the possibility to scale this to a global scale. Then third is the computational and atmospheric constraint. So albedo is also estimated in a traditional way using the physics-based model, which are based on BDRF-based retrieval method, which are computed not only computationally intensive, but also requires a lot of data or a lot of points, a lot of parameters from the field, or I would say from the region, which makes it hard to scale up to a global scale. So in this study, what we focus is we develop a high resolution albedo framework, Basically, we use machine learning algorithm and Sentinel-2, existing Sentinel-2 data, and along with the modest albedo product to downscale like albedo from 500 meter to 10 meter resolution, so that those variability or details which were missing can be captured using high resolution albedo product. We compared like two artificial intelligence algorithm or machine learning algorithm. One is the machine learning algorithm, that is random forest, and the second one is the more advanced deep learning algorithms called neural networks. And we did hyperparameter tuning. We tested for generalization and make sure it is suitable for different land cover classes. Then we also assess the cross-temporal transferability. What if we train our model for a single year data and completely predict albedo using the trained model? If we predict the albedo for completely unknown year, whether it's able to capture those peculiarities in details, or it is somehow it is missing out some of the details. Fourth is we also develop a pipeline to scale up this method to a operational scale, depending on the compute resources, so that people can use this information, download those albedo products, and use in different applications from agriculture to urban heat island to climate change studies. So when we were designing this study, the first thing that comes to the mind is um, like what is a study area we should really choose to test this hypothesis or test these objectives. Um, so we took Oregon. We decided to stick to Oregon state in United States. And the reason why we have chosen this study area is very heterogeneous. It's very diverse in terms of land cover. You can see the land cover map on the right, top right, where it has all the prominent land cover classes. And vegetation is one of the largest land cover class in this area, um, governed by other classes. Uh, then this is also very variable in terms of topography, which makes this place a ideal place to test our algorithm. Also, Oregon has all the climate conditions and the weather throughout the year. So if something is working for Oregon, it should work for other parts of the world as well. So we use a lot of points for training. Basically, we use the entire time series data from 2000, 2001, um, from all Sentinel-2 bands daily, every say 6 days repeativity, along with modest data. We collected over 65 million sample points, which is used for training the model, validation, and testing. We also carried out-of-year testing, out-of-year evaluation with 2000 data with 45 million points. And how we calculated accuracy is using the different statistical methods like R-square, RMSE, p-bias, and unbiased RMSE. R-square is basically gives you the correlation, tells you the correlation between the predicted versus actual, whereas RMSE quantifies the actual error in the data, in the prediction. We also perform experiment with different sampling strategy ranging from random to non-stratified sampling strategy to come up with this. And this is the distribution here about the number of training points, the number of sample points used for training the actual model, AI model, versus validation and testing. So on the x-axis we have different land cover, and on the y-axis we have number of sample points used for this study. So this is the overview of the methodology. The main input for the study is basically the satellite data, basically the Sentinel-2 bands, which is a 10-meter spatial resolution. Along with Sentinel-2 bands, we also use SRTM-DM, that is a digital elevation model, and we derive three different indices out of it, basically the slope, aspect, and hill shade. And we also use modest albedo product at 500-meter resolution because we don't have ground data. And the idea is to downscale these 500-meter resolution to 10-meter spatial resolution to capture those details which are missing in 500-meter resolution. From Sentinel-2 imagery, we also calculated different indices, biophysical indices, which have more relevance to vegetation, water, and different biophysical things. Um, yeah, as I said, from SRTM, we derive elevation, slope, aspect, and hill shade. We stack the Sentinel-2 bands and SRTM band together, entire time series for a single year, and basically resample it to a to match the modest 500-meter scale. Then we perform model training using two AI algorithms. One is the machine learning random forest algorithm, and then second one is the neural networks, which is a deep learning algorithm. So we divide the database into three categories: training, testing, and validation. We perform hyperparameter tuning to identify the best possible parameters for these models. We did, and then we also did a bootstrapping to ensure that whatever we are running, what is a model uncertainty, and whether how much deviation in terms of accuracy we are getting. And we also did some kind of a feature importance analysis, which tells about what features in the input features are really important for the model prediction. Um, and then we actually, with the trained model and availability of high resolution Sentinel-2 images on all those biophysical parameters, we actually predicted and developed a pixel-based 10-meter albedo product using the random forest model. And so the final products are random forest model, the 10-meter high resolution albedo product, and the feature importance, which tells what features are important for this study. We also come up with a model performance and accuracy assessment report, which tells the performance of the different models for different distribution. Here's the difference between random forest and neural network model and how it works. So random forest is basically an ensemble-based, shallow machine learning model based on decision trees. And each tree predicts its own output, and the output from all the trees are combined um, based on average voting to come up with final prediction. This is the strength of the random forest model is it can handle the non-linear relationship pretty well. It is robust to noise and outliers. Remote sensing community or in real world scenarios, outlier and noisy data is very common. So random forest is pretty good for that. It works pretty well with small data set, so we don't need ample amount of data set to train random forest model. Even if we have small chunk of data, we can use this model for prediction. This is The random forest model is also more interpretable as compared to deep learning model, which is kind of a black box. So this is about the random forest machine learning model. And the neural network model works completely in a different way. It is actually inspired by the human brains, and how it works is we have the input layer, which have all the features. Then we have hidden layers, and then we have output layer, or and the prediction is we get prediction out of after the output layer. And how these hidden layers and input layer and how output layer are connected is these are connected with different neurons. And how the neural network works is it tries to balance the weight or adjust the base based on the predicted value, and it's a iterative process. And the main goal is to minimize the loss function, or I would say, and loss function can be RMSC and other things. And the strength and limitation of this model is the neural network requires a lot of data from the field, because it is based on deep neural networks. It is sensitive to hyperparameters, so we have to tune the hyperparameter um, in a very specific way. Otherwise, the accuracy deteriorates for neural network. It also captures the non-linear relationship, and it can be sometimes overfitting in case of, it can also overfit the data in case of noisy data. So overall, for our study, we found that random forest model works pretty well in terms of albedo prediction versus neural network model. And one of the reason why it is performing well as compared to neural network is because in real world scenario there are a lot of outliers and noise in the data, and random forest is well capable of uh, handling these outliers or noisy data. These are the results from the study. This is actually figure A represents the trained accuracy, or I would say in-ear accuracy. When I say trained accuracy, that means the model is validated using the same sets of points used for training. Then we have test accuracy. Test accuracy means that we have tested this algorithm using unseen data, but from the same year. Whereas test accuracy, figure C represents the out of year test accuracy. That means the model is validated against the data from different year, and it is the data set is not at all seen by the model. We can see that for the random forest model, on the x-axis we have modest albedo, and on the y-axis we have a random forest estimated albedo. And we can see that the model is doing pretty well in terms of R square and RMSE. The correlation is for the training is pretty high, around 0.97, with only 6% error. Whereas for in-year distribution, um, the R square reduces to 0.90, and the accuracy also deteriorated, and the error increased to 10% now around. And for the out year distribution, the errors are much higher as compared to in-year distribution, which also makes sense because we are not accounting for the seasonality or seasonality. We are accounting for seasonality, but we are not accounting for interannual variability here. Probably we need to train the model with more year of data, um, capturing drought and flood events to counter that. We also calculated the accuracy for neural network, and we found that the performance for neural network, both training and testing, for in-year and out-year distribution is slightly lower than the random forest model. And one of the reason why we have um, less accuracy as compared to the random forest model is because in real world scenario, there's not of outliers and noisy data, which random forest is capable of handling in a nice way than the neural network model. This is the graph shows the feature importance or variable importance. variable importance, something, what features, input features are most important for predicting the land surface albedo. So on the x-axis, we have Gini score, which is a measure of how much importance is there. And then on the y-axis, we have input feature. We can see that band number 5, which is in a red edge band in Sentinel-2 data, is one of the most influential predictor, contributing almost 67% for the model variability or model importance. And this is likely because of the dominance of vegetation features, vegetation land cover class in our study area, vegetation governed by vegetation structure, chlorophyll content, and canopy structure. Whereas band 4 to band 6 also showed a pretty good importance, contributing around 8.4% um, contribution to the model. Whereas we can see like top top spectral bands, band number 2 to band 8, almost account for 73% of the explains the 73% of the model variability. There's one more interesting thing that the indices which are derived using these bands have shows the low variable importance. This is because these are a byproduct of the original Sentinel bands. So most of the variability is captured in the original bands rather than the indices. That's why these are having low Gini score importance. This is a very interesting map from our study. Basically, the map which shows the high resolution albedo product. So on the left hand side, we can see a big window showing the high resolution albedo product at 10 meters spatial scale derived from Sentinel-2 images. Um, and the albedo varies from 0.01 to 0.03, whereas these subfigures shows the different areas or different regions in the study area. So we basically collected or investigated three regions in the study area to find out how albedo is captured using high resolution albedo product, which was missing in coarse resolution modest product. So A1, B1, and C1 shows the albedo what we have estimated using our high albedo product derived from Sentinel-2 data, whereas A2, B2, C2 is actually the derived albedo from modest data, which is already available at 500-meter scale from for the location A, B, and C. And whereas A3, B3, C3 is actually the false color composite image of Sentinel-2, which shows the how in reality this location looks like. So red is actually the vegetation cover in the area, whereas A4, B4, and C4 is actually the land cover map from NLCD data, which is pretty high resolution and just used for understanding how these albedos, which are not captured using modest data, is well captured using high resolution Sentinel-2 derived albedo product. And we can see that here the agriculture areas in figure C. If you see, the agriculture areas are albedos from the agriculture areas are well captured in the high resolution product, which was completely missing in the modest albedo product because of the mixed pixel issue. And you can see that how these different agriculture fields, some are planted, some are fallow, uh, how how different are albedos from these different agriculture fields, which are captured by our high resolution albedo product and missed by this Sentinel modest albedo product. So this is the graph which shows the variability, what variability it can capture what variability is captured using high resolution 10-meter sentinel to derive albedo product, and what is missing in albedo modest derived 500-meter albedo product. So on the x-axis we have different land cover classes, and on the y-axis we have albedo values. So the solid box plot represents the modest here at 500-meter scale, and the dash lines represents the high resolution. Slanted dash line represents the high resolution sentinel to derive albedo at 10-meter. And we can see that in all the land cover classes, the sentinel-2 data or the albedo derived from sentinel-2, we can see there is a high variability as compared to the modest 500-meter resolution albedo product. This is because modest is producing a mixed pixel, and because of that, this variability cannot be captured using modest product, and where this high resolution product can really be a game changer for understanding the variability and interactions between different land cover classes and how albedo responds to different land cover classes. This graph shows the seasonal variability of modest albedo and sentinel albedo for representative land cover classes, mainly the croplands, green, broadleaf forest, mixed forest, urban and built-up. So on the x-axis of the each graph is the timestamp. So we extracted the data from 2016 and 2025 for different days. And we plotted the time series from modest 500-meter spatial resolution and sentinel to derive albedo at 10-meter spatial resolution. And we found that the seasonal characteristics are also well captured in sentinel to derive albedo product, which is also one kind of a validation method uh, to say that this is performing pretty nicely. This is an example of urban and built up, and the difference here is, so the red one is actually the albedo from Sentinel-2, and the blue ones are the blue is actually the modest albedo. And here we can see that there's more variability in red than blue, and one of the reason why it is so is because Sentinel-2 is able to capture those variability within the glass, which was missing in the modest derived albedo product. So the main conclusion of this study is we developed a operational machine learning framework to generate albedo at 10-meter scale by integrating Sentinel-2 imagery and modest already existing modest albedo product. We achieved high performance in terms of accuracy, RMSE of 11.83, 11%, which is pretty good. The random for model, the random forest model outperformed the neural network model. And the primary reason is because new random forest model is more generalizable and more immune to noisy data than the neural network model. Um, and we have also seen that the model can be transferable to different years, because as we have done a thorough investigation on computing using the same trained random forest model to predict the data for completely unseen year, and the performance was slightly lower than the in season distribution, but it was not significantly low. Uh, and our analysis also revealed that visible and near infrared region bands are the primary driver for broadband albedo estimation. This is the application area. I think I have shown this in my earlier slide, but I just want to focus is using this product. I really want to investigate the urban heat island effect. People in a lot of South Asian countries are painting their rooftop as wide. So I would really want to study how high resolution albedo product can be useful to study whether this is an effective, this solution is a effective solution, or we are just wasting money and painting the white rooftop is a myth. The second thing is agriculture monitoring. I really want to see how high resolution albedo product is useful to account for carbon budget, basically the rising temperature because of tillage versus non-tillage crop agriculture management, agriculture cultivation practices. I also want to study the ecosystem services and also see like how high resolution albedo can be useful for improving the climate models or to study the climate change or future trends. These are the future directions. So far we have come up with a great product, but there is nothing called great. There's always a scope of future improvement, and one of the future improvement we want to do is in the current framework we have not done any kind of a feature engineering. That means number of features that we are using for training is unrestricted, and we have included all the features, input features that we can think of for model for training our machine learning model. But in future we would like to do some kind of future engineering which can also significantly reduce the computational cost, but also can be useful for predict or improving the accuracy. We would also like to use advanced deep learning method with temporal information preserve. Uh, Random forests cannot preserve the temporal information, whereas advanced deep learning algorithms like convolution neural network, long short-term memory, and convolution neural network, along with coupled with short-term memory transformer, these models are pretty well, which can actually preserve the temporal information. This can be useful for improving the accuracy of machine learning model. Then we also want to use the foundation models to experiment how foundational models can be useful, or pre-trained models can be useful for improving the accuracy of albedo product. And lastly, we would like to develop a dashboard so that this data is available to users and on a global scale with 6 days repetitivity for now. And then so that these data sets can be used by the users from different community uh, to investigate climate change, applications on agriculture, urban heat island, and those kind of things. So this research also supports sustainable development goals, which is very important for the planetary health, um, such as zero hunger, good health and well-being, sustainable cities and communities, and climate change action. I would also like to acknowledge Dr. Hamid Al Mahmood and Dr. Christopher Williams, who was my postdoc advisor at Clark University, for shaping this work. Um, this is all from my side. Thank you very much for listening to my talk today. And I would like to end the talk with a quotation, or I would say a poem, that rising temperature, burning air, climate changes everywhere. Not too early, not too late. It's time to change our fate. Thank you very much, and I'm open for any questions, suggestions, and collaboration.
All right, thank you so much, Dr. Tiwari, for that insightful look at how we can bridge the gap between massive planetary satellite data and the hyperlocal environmental realities we experience every day. I think for me personally, the most interesting part was seeing how downscaling our view of Earth's albedo from 500 meters to just 10 meters using AI can unlock such actionable insights for everything from urban heat in islands to global food security. I would suggest opening up the Q&A session. I'll kick things off with a question on my own, and then we'll continue with the ones from my colleagues and our audience online. So in your research, you noted that the random forest model actually outperformed the neural network architecture. So given how popular deep learning and neural networks are right now in geospatial AI, why do you think a tree-based model handled this downscaling task better than deep learning?
So tree-based model is based on the ensemble approach. That means so individual trees predict the output, predict each output. So suppose there are 500 trees, they will be output predicted from all 500 trees, and it works on the averaging. So all the output will be average and combined for the final prediction, which is not there in the deep learning model. So in random forest model, if there's a noisy data, and since it is an averaging problem, then the noise is actually suppressed. Whereas in deep learning model, it's like a feedback which is used to improve the model performance. So noisy data can actually overtune the deep learning model. So that's the reason why we are getting more, more in terms of high accuracy as compared to deep learning model.
Perfect, thank you. Any questions from the Inwood team? Yeah, Dr. Mateen?
Yeah, thank you, Varun, for presenting very interesting study that you are working on. I have two technical questions, but I'll pass that for now because we don't have enough time. So I would like to know about the status of the product. So now you have tested in Oregon, and then what is the next state plan from the Clark Geospatial Lab? So we want to compute it for the global data set and make it available for everyone to download. What is the plan for that?
So the idea is to come up with a global product at 6-meter scale for now. So we are also collaborating with different research groups in different thematic areas like agriculture, urban heat island, like urban group, climate group, to validate whether these product or high resolution albedo product adds value or not, to also have to get some feedback from the users perspective of user community. Once we finalize that, we can actually scale up this model to a global scale and probably develop a dashboard so that these data sets are available to all the users across the globe.
Have you done any validation of instrumental data, or is the validation only from again the model?
So currently, because the flux tower data is very limited in US, and it is also quite old, so it was very hard to get the flux tower data to have the ground validation. Whatever validation we have carried out is using the same modis albedo product, because in some ways we are actually mimicking the modis albedo. That's a reference to test our algorithm. But in the near future, once we have more collaboration, um, once we have the data from the field, we can also do some systematic validation using the ground-based data, but that's going to happen for only a point location, not for the entire time series or spatially explicit way.
Yeah.
Hello. Hi. Thank you so much for your talk today. It's very insightful. I just wanted to ask, your focus, your focus is very much on urban science systems and basically reducing emissions. Do you think there's any possibility that your AI algorithms could be focused on perhaps revitalizing the Earth's natural reflective systems like earth sheets or forests? Do you think there's any research possibilities in the future for that?
Can you please repeat your question? It's not very well audible.
Oh, sorry. I'm asking if there's any future in research around revitalizing natural reflective earth systems such as ice sheets and forests.
Yeah, surely this is the future work. So the idea is actually to create a product first and then to investigate the use of this product in different application areas. So in future, we will focus on using this product for glacier monitoring, ice monitoring, or other natural resources management.
Yeah. All right. We are running out of time, but thank you so much for your presentation today. It was very insightful. And for everybody listening, in case you miss anything, feel free to watch our video shortly uploaded on our website or on our YouTube. And yeah, and I hope to see you next week. Thank you so much.
Thank you, everyone.